Hello students, in this video we will discuss the working of Hartley oscillator and also we will derive the expressions for frequency of oscillation and condition for oscillation of Hartley oscillator. Hartley oscillator is a type of LC oscillator which produces sine wave in the range of radio frequencies. So it is called as high frequency oscillator or radio frequency oscillator. As we discussed in the previous video, a LC oscillator which uses two inductors and one capacitor in its feedback network, it is called as Hartley oscillator. This is the amplifier stage which uses an active device as a transistor in common emitter configuration. The voltage divider resistors R1, R2 and emitter resistor RE are providing necessary biasing to the circuit so that transistor can operate in its active region to amplify the signal properly. RFC is the radio frequency choke. The reactance of the RFC is very high for high frequencies, so it can be treated as open circuit. While for DC conditions, the reactance of the RFC choke is 0, so it allows DC to pass through it and blocks transient AC signal. Hence, it provides isolation between AC and DC operation. CE is the emitter bypass capacitor which avoids the negative feedback given to the circuit. CC1 and CC2 are coupling capacitors. The CC1 is used to couple the output of the transistor amplifier to the feedback network, while the CC2 is used to couple the feedback signal to the input of the transistor amplifier. Common emitter amplifier provides a phase shift of 180 degree. As the emitter is grounded, the base and collector voltages are 180 degree out of phase with each other. As the center of L2 and L1 is grounded, the voltage at the point 1 is 180 degree out of phase with the voltage at the point 2. Hence, the feedback network also produces an additional phase shift of 180 degree. Thus, the total phase shift around the loop is 360 degree or 0 degree, which satisfies the required condition for oscillation. When the power supply is switched on, the capacitor C starts charging towards VCC. When the capacitor is completely charged, it starts discharging through the inductors L2 and L1. Because of this, current flows through the inductors L2 and L1. So due to the current flow, magnetic field will be set up around the inductors. When the capacitor is completely discharged, the maximum current flows through the circuit. At this instant, the electrostatic energy in the capacitor is converted into magnetic energy in the inductor. Now, the magnetic field starts collapsing. As per Lenz's law, a back EMF will be introduced, which charges the capacitor with reverse polarity. When the capacitor is completely charged, the magnetic energy is converted into electrostatic energy. Now the capacitor once again starts discharging through the inductors, but the direction of the current is opposite to that of the direction of the current earlier. Once it is completely discharged, electrostatic energy is converted into magnetic energy. This process repeats. Thus, charging of capacitor with alternate polarity and discharging produces alternating current, but the amplitude of the signal is low. The voltage across the L1 is applied as the feedback signal and it is amplified. Once again, the amplified signal is fed to the feedback network and it is continued so that the circuit adjusts itself to get A beta equal to 1, resulting into self-sustained oscillations. To understand the working of LC tank circuit with step-by-step diagram, you can refer my earlier video named Working of LC tank circuit. To derive the frequency of oscillation and condition for oscillation, we will write the general expression for LC oscillators, which was derived in my previous video titled General Equation of LC oscillators. We know in Hartley oscillator, Z1, Z2 are inductors and Z3 is a capacitor. We'll substitute Z1 is equal to j omega L1, Z2 equal to j omega L2 and Z3 equal to minus j by omega C. Here Z1 is replaced by j omega L1, Z2 is replaced by j omega L2. In the second term, Z3 is replaced by minus j by omega C, Z1 is replaced by j omega L1 plus Z1 Z2 is replaced by j omega L1 j omega L2 plus HIE into Z1 Z2 Z3 are substituted here. J into J is minus 1, it becomes minus H of E omega square L1 L2. Here J into J is minus 1, minus into minus is plus, omega is getting cancelled, so it becomes L1 by C. Here in the third term, J into J is minus 1, it becomes minus omega square L1 L2. Here in the fourth term, we will take j omega commonly out. So it becomes HIE j omega into L1 plus L2 minus 1 by omega square C equal to 0. Here we will equate the imaginary part to 0 to find the frequency of oscillation. The imaginary part is HIE omega into L1 plus L2 minus 1 by omega square C equal to 0. We will write now L1 plus L2 is equal to 1 by omega square C. We'll bring omega square to other side. It becomes omega square is equal to 1 divided by L1 plus L2 into C. We'll find out omega. So we'll have to take the square root of it. Now we will replace omega by 2 pi f and find f, which is equal to 1 by 2 pi square root of L1 plus L2 into C. F is equal to 1 by 2 pi square root of L equivalent into C, where L equivalent is L1 plus L2. This is the frequency of oscillation of Hartley oscillator. Now we will equate the real part to 0 to find the condition for oscillation. This is the real part of the general expression which we made equal to 0. Here the first term and the last term are brought to the other side, so sign becomes positive. Now let us take omega square L1 L2 commonly out between the first term and the second term. So it becomes omega square L1 L2 into 1 plus h of e equal to L1 by C. Now we'll substitute omega square which was found in the previous slide. Omega square is replaced by 1 by L1 plus L2 into C. The remaining terms are written as they are. After simplification, it becomes L2 into 1 plus h of e divided by L1 plus L2 equal to 1. We'll do cross multiplication. It becomes L2 into 1 plus h of e equal to L1 plus L2. We'll divide this expression by L2. So it becomes 1 plus h of e equal to L1 by L2 plus L2 by L2 is 1. We'll cancel the 1 on both sides. Now h of e becomes L1 by L2. This is the value of h of e required to satisfy the condition for oscillation. Applications. Hartley oscillators are used to produce a sine wave with the desired frequency. They are used in general purpose applications like signal generators. They are also used as a local oscillator in radio receivers. They are suitable for oscillations in radio frequency range up to 30 MHz. Advantages. They are easy to tune. Very few components are needed, including either two fixed inductors or a tapped coil. The frequency can be varied over a large range as per requirement using a variable capacitor. The amplitude of the output remains constant over the working frequency range. The feedback ratio of the tapped inductor remains constant. Disadvantages. It cannot be used as a low frequency oscillator because high value of inductors are not possible practically. The harmonic content in the output of this oscillator is very high. So it is not suitable for the applications which require a pure sine wave. Thank you.